Well, welcome. In this video, we're going to be looking at scale changes of trigonometric functions. And we've looked at scale changes already. This is going back to the previous chapter where we've already talked about scale changes, but we're going to look now to see how scale changes can affect our trig functions and how we can use those scale changes to be able to find out and draw out pieces of information that we need to know. But let's review what exactly a scale change is. So here we have one particular scale change, that's 1/2 x and 3y. I want you to think for a minute, and I want you to think about what impact or what influence does that scale change have on the graph. Now remember, this is a scale change. A translation is where it's moving to the left, right, up, or down. A scale change is where it can be stretched horizontally or be stretched vertically. So that's what's happening here. So I want you to take a second and think what's going on. Are you thinking about it? Well, here's what you should have thought of. You should be thinking that horizontally, the graph, in this case, since it's 1/2 x, the graph is actually being shrunk horizontally by 1/2, and it's being stretched vertically by 3. And one of the things that we need to remember is that when we're looking at a rule, that's what we have here. We have a rule, 1/2 x and 3y. That is a rule. That is telling us exactly what's happening. You don't have to worry about taking the reciprocal or doing the opposite of anything. You don't have to do anything like that. Take and read it or look at it exactly as the way it is in the rule. So the rule tells you exactly what's happening. So it's 1/2 of x, so it means it's being shrunk horizontally by 1/2. It's 3y, so it's going to be stretched vertically by 3. Now let's think about what impact that would have on a function. Let's say if we're looking at the equation y equals x squared. And we want to come up with a new equation after applying that scale change. Well, remember with that scale change theorem, we would take, or the graph scale change theorem, it means that we take and replace the x with the reciprocal or the opposite of what's happening with the x, and replace the y in our equation with the reciprocal or the opposite of what's happening with the y. So if I did that here with y equals 3x squared, here would be my result. Now I would have y divided by 3 equals 2x squared. Or another way to look at that is we could say that it would be y, if I get the y by itself, it's the same as y equals 3 times the quantity 2x squared. Now how does that apply to trigonometric functions? Well, that's what we're going to look at now. So we're going to look at how this same scale change would affect our sine function here. We'll look at some graphs. We'll look at some other pieces of information that we need to know where we're going to apply what we know about scale changes to our trigonometric functions. So let's look at this one now. Okay, so here we have y equals sine of x. We want to figure out what effect does a scale change have on its graph? Well, it's going to have the same impact. It's going to still have a horizontal shrink of 1/2 and a vertical stretch of 3. Now, if you recall for our sine function, though, our sine function will look something like this, between 0 and 360. So one cycle for our parent function, sine of x, repeats itself every 360 degrees. Well, if this is going to be shrunk to be half the size, so now instead of being having a cycle of 360 degrees, it's going to be half of that. It's going to be 180 degrees. And if you think about our parent function here going between -1 and 1, if it's going to be stretched vertically to be 3 times larger, it's now going to go between -3 and 3. Now how is this going to affect our equation? Well, our equation will be, it's going to affect it the same way as it did for our parabola. We're going to replace y with y divided by 3. And we're going to replace x with 2x. So y equals sine of x would now be the equation y divided by 3 equals sine of 2x, which it's actually better to write it with the y by itself. So we're going to write it as y equals 3 times the sine of 2x. That would be our equation. And so remember, when you're writing out the equation, you always take the reciprocal or take the opposite of what's happening with the x. But then with the y, if you want to get the y by itself, you can just do the same thing as it was originally. So we can write it as 3 times the sine of 2x. Now if you notice, I have the graph here for us already for y equals 3 times the sine of 2x. So remember we said that the normal, oops, I guess it's a little bit too big. The normal graph for the sine function would go between 0 and 360 and would go between -1 and 1.
But this graph has been shrunk horizontally to be 1/2 the size. So now instead of one cycle going from 0 to 360, it's now going from 0 to 180. And you can see that the graph, the maximum or minimum values now, instead of going between -1 and 1, they go between -3 and +3. Now from this graph, there's a few pieces of information that would be good to look at. The first of which is a new term. This new term here is called the amplitude. And that's the distance, as they're drawing here, from the center line, some places will call that the equilibrium, to the maximum value, or the way that our book describes it, it is 1/2. So it's half the distance between the maximum and the minimum. And for this problem here, our distance between the maximum and minimum are -3 to 3, so that distance is 6 units. Well, half of that would be 3 units. So for this one, our amplitude is 3. Or you can look at it as it's going from our equilibrium, our center line is 0 up to 3, so our amplitude would be 3. The period, we've talked about that. That's another term, though, that they're defining for us as far as how to find it in this next box. But the period, remember, is how far or how long it takes for it to repeat itself, or the period is just the length of one cycle. And in this case here, it would be 180 degrees, or if we were working with radians, that would just be pi radians. Now remember that the scale change, the rule for this particular function was that x was going to be shrunk by 1/2 and y was being stretched by 3. Why do I say that? Well, let's look at our amplitude and period, because we're not always going to be given the graph. But what if we were just given an equation or just given the information to know what the amplitude and the period would be? We want to figure out, well, how can we get that from maybe the scale change? Well, if I have the scale change of 1/2 x and 3y, if you notice, my amplitude is the same as the number that's in front of the y. Well, that's significant. And the period, if you think about it, the period is 180 degrees, which is half of 360, or pi, which is half of 2 pi. Well, if I look up here, this value here is saying that's taking half of whatever x is, so 1/2 of 360 would be 180, and 1/2 of 2 pi would be pi. So those pieces are significant, and here's why. If we look down at this box, it's defining for us, and this is important, that the amplitude is the absolute value of b, and the period is 2 pi times the absolute value of a. Seems kind of weird. Why would they use, if they're going to use a, wouldn't they use for that for the amplitude? Maybe use b for the period. Why wouldn't they do that? Well, they're not abbreviating here. What they're doing is they're looking at our original equation or representation for a scale change, is that it's a times x and b times y. And remember up here we said that the amplitude was the same as the number that was in front of the y. In this case it was the 3. Well, that's what they're saying for this rule. It's always going to be the absolute value for the amplitude. It's always the absolute value of whatever's in front of the y. So it's always going to be a positive number, in other words. And the period is always going to be 2 pi times whatever a is, or 360 times whatever a is. Now let's talk about that for a second, because a lot of what we're going to be doing now is going to be in radians. So just make sure you're aware of that we're going to start to shift more to be working with a lot of radians, because it's easier to deal with radians, because it's easier to remember pi and 2 pi and 3 pi and 4 pi and so on, instead of 180, 360, 540, 720. Those are a lot harder to remember than just the multiples of pi. So we'll work with a lot of radians now. But anyhow, so the period is found by taking 2 pi times whatever that value for a is, whatever's in front of the x in our scale change rule. So how can we apply that? Let's look at this equation. Here we have y equals 6 times the cosine of x divided by 3. And they're asking us how this function is related to the parent function, which would be the cosine function in this case. Well, we want to come up with a scale change for that. even if they didn't ask us for us. You just want to be in the habit of always looking for the scale change, because that's going to tell us a lot of useful information. So the scale change, we take the opposite of what happens to the x. Well, x divided by 3 would be 3 times x. Or you can look at that as being the reciprocal of what's happening with the x. So 1/3 x would be the same. The reciprocal of that would be 3. And then for the y, we're just going to take whatever number's in front of the cosine here, the 6, and that's how y is being affected. So 6 times y, or if we were to put this in our equation with the y, we would take y divided by 6, which again is the same as 6 times the cosine of x divided by 3. So this is our scale change. Our scale change here is 3x and 6y. What does that mean? Well, that means that the graph is going to be stretched horizontally by 3 and vertically by 6. So when we go and try to find the period, it's really important to think about what's happening here, to visualize in your head that, remember, the cosine function typically would go from 0 to 2 pi. Well, if it's stretched to be 3 times wider, or stretched horizontally by 3, it's now going to go from 0 to 6 pi. So the period would be 6 pi. Algebraically, we could use this theorem to say that it's going to be 2 pi times a. Well, a in this case, or the absolute value of a, is 3, and 2 pi times 3 is 6 pi. So there's your period. The amplitude is always whatever b is. Well, b is the 6 here, so our amplitude is simply 6. So it has an amplitude of 6 and a period of 6 pi. And again, the reason why the amplitude is 6 is going from that center line up to the maximum value would be a distance of 6 units. Because originally it was a distance of 1 unit, but it's stretching out to be 6 times larger. So now it's going to be a distance of 6. Let's look at another one together. This one's kind of tricky because this one here, we have some decimals and some fractions, so it gets kind of funky. So what we're going to do, again, is first figure out what's the scale change. The scale change here would be, we take for the x, we take the reciprocal of what's happening with the x. So here I have 4/5. Reciprocal of that would be 5/4. So you can say 5/4 x or 5x over 4. Either way, it doesn't matter. And then for the y, we just take the same as what we have here, the 3.5. So it's just going to be 3.5y. So that means it's being stretched horizontally by a factor of 5/4, or 1.25. And it's being stretched vertically by 3.5. So to find its amplitude and its period, I always like to find the period first, only because it works with the a value, the first value there. So the period is going to be, I always take 2 pi times our a value, which is 5/4. Well, when you multiply those together, you get 10 pi over 4. Reduce that, because you always want to reduce our fractions, and you get 5 pi over 2. So the period would be 5 pi over 2. The amplitude is just whatever b is. B is 3.5, so our amplitude is 3.5. So let's look at some graphs now. So here it says the graph to the right shows an image of the graph y equals sine of x under a scale change. Find an equation for the image. So this is so something's happened with our sine function here. We want to figure out what the new equation would be. But there's something really different about this one. Take a second and look at it. Remember and think in your head of what the graph for just a plain old sine function would be. Yes, I know this is being shrunk and shrunk horizontally and stretched vertically, but do you notice anything else that's really different about this one compared to the parent function for the sine function? Well, what you should realize is that with the sine function, you would start at 0 and go up to 1, but this one's starting at 0 and it's going down. That's pretty significant. What would make a graph flip? Because that's essentially what's happening here. The graph is flipped. Well, a negative would make a graph flip. Because if you think about the graph y equals x squared, when it's a positive, it's pointing upwards. When it's a negative x squared, it's going to point downwards. So here, our answers, our equations, can involve a negative because it's being flipped over the x-axis. So in our scale change, we'll represent that with a negative sign. Now we got to figure out, well, what's happening horizontally? Well, I kind of gave it away. It is being shrunk, and if you notice, we have every 45 degrees are being marked. So this would be 90 degrees. This would be 180. So one cycle here happens at 180 degrees, which is half a 360. So you can say it's x over 2 or 1/2 x. And horizontal, or vertically rather, we could easily see that it's being stretched to be 4 times larger, so it's going to be 4y. That's not what they're asking for though, but we always want to find the scale change. That'll help us come up with our equations or anything else they're asking for. So our equation is going to be in the form y equals, so for the y, it's going to be 4 times the sine of x, but it's a negative, so we want to make sure that we include that. So it's a negative 4 times the sine of, and replace this x with the reciprocal of 1/2, so that's 2x. So there's your equation. So again, you want to make sure that you remember to include the negative there. So why don't you guys go ahead and try this next example on your own. So why don't you pause the video. I want you first to figure out what is the scale change though that's happening here. So figure out what the scale change is and then use that to come up with the new equation for the cosine function. By the way, this line that's down here, that's, I don't know how that got on there. That wasn't meant to be there. This is your x-axis. And this, they're just showing you what the parent function would look like for the cosine function. So in other words, we can see that it starts at 0 and first cycle ends at 2 pi. Don't really need that though, but I want you to come up with the equation. That's your ultimate goal, the equation for that bold line there. So why don't you pause the video and hit play when you're ready to check to see if you have the correct answer. Well, you should have realized that horizontally this is being stretched to be 3 times larger, because originally it went from 0 to 2 pi. Now it's going to 0 to 6 pi, which is 3 times larger. And vertically it's being stretched all the way up to 3, so it goes from 0 to 3 instead of 0 to 1. So it's being stretched vertically by 3 as well. So your scale change, your rule for your scale change would be 3x and 3y. So writing it as an equation, it would be y equals 3 times the cosine of x divided by 3. There's one more thing we're going to talk about, and that's this idea of frequency. Now, this is a really important term to make sure you understand. The frequency, to figure out what the frequency is, it's going to be the reciprocal of the period. So remember that the period is represented by 2 pi times our a value in our scale change. And our amplitude was another term that we dealt with. That was our b value in our rule for our scale change. Well, the frequency is the reciprocal of whatever the period is. And it represents the number of cycles the curve completes per unit of the independent variable. Thus, the frequency of the cosine function is going to be, well, let's figure that out. Well, first, the period for the cosine function is 2 pi. Every 2 pi, it repeats itself. Well, the reciprocal of that is 1 over 2 pi. Now, it's important that you write this correctly. It is not 1/2 pi. Okay, it's 1 divided by 2 pi. So the pi needs to be in the denominator. Now, what does that represent? Because it's important to understand what this really means. This means that we have 1 cycle per 2 pi, which makes sense because the frequency refers to how many times something occurs. So the frequency here for this function is it occurs once every 2 pi, so 1 per 2 pi. There is a question that we looked at earlier. Let's go back to it. 1b, where we had the period of 5 pi over 2. Well, the frequency of that would be the reciprocal, which would be 2 over 5 pi. What does that represent? Well, it's 2 cycles per 5 pi. So every 5 pi, this particular function would repeat itself twice within that 5 pi. So there's 2 cycles for every 5 pi. Let's look at this example. So to start out with, we first want to figure out, well, what's the scale change? Well, the scale change for this would be that it's, for the x value, it's going to be 3 times x. For the y value, it's going to be 6y. Well, for the period, all we're concerned about is the value for a. So the period for this one would be 2 pi times our value for a, which is 3, which is 6 pi. So the frequency would be the reciprocal of that, 1 over 6 pi. So that means there's 1 cycle every 6 pi. That's how we'd interpret that answer. Well, that's it. So there's a lot of terms that we talked about today. We talked about amplitude, we talked about period some more, and we talked about frequency. And the most important thing is to remember that anytime we're working with these problems, it's always best, the best way to approach this is to figure out first what is your rule for your scale change, and then interpret everything based on that. So with that, good luck now as you work on your assignment.